Stars are big, bright balls of hot gas. You knew that. But before a star is big, bright, or hot, it's none of those things. It's a cold, dark clump of dust and gas floating in space, doing absolutely nothing, until gravity shows up and ruins everything. Protostar. So here's how a star is born. You take a cloud of gas and dust, mostly hydrogen, and you let gravity slowly pull it inward. As it collapses, the center gets denser and hotter, and eventually you get a protostar. Think of it as a star embryo. No nuclear fusion yet, no shining, no drama. Just stuff falling inward. And the youngest ones, called Class 0 protostars, are basically invisible. You cannot see them with a regular telescope because they're buried under a massive envelope of gas and dust that actually outweighs the baby star itself. All their energy comes out as far infrared light, wavelengths around 60 to 100 micrometers. Your eyes? Useless. The luminosity you do detect isn't from fusion, it's from material slamming into the protostar as it feeds, pulling in surrounding gas at roughly 10 to the negative 7 to 10 to the negative 9 solar masses per year. Accretion is the engine here. Gravity is doing all the work. This buried phase lasts only about 10,000 years. By class 1, around 100,000 years in, the star has eaten enough of its cocoon to finally peek through. A sun-like protostar gathers most of its final mass within about 1,000,000 years. The universe's biggest construction project assembled in the dark, and you can't even watch it happen. So now we have a baby star with a belly full of hydrogen. What happens when the core gets hot enough to actually ignite? Main sequence star. So the core hits about 10 million degrees, hydrogen starts fusing into helium, and the star turns on. Like, fully turns on. It's now producing its own energy, pushing outward with radiation pressure, and perfectly balancing against gravity trying to crush it. This stage is called the main sequence, and it's where a star spends the vast majority of its life. The sun is a main sequence star right now, has been for about 4.6 billion years, and it'll keep going for roughly another 5 billion. Pretty chill. But here's what's wild. Main sequence sounds like one category, but the range inside it is absurd. A tiny red dwarf at 0.1 solar masses burns so slowly it can last about 2 trillion years. That's over 150 times the current age of the universe. Meanwhile, a massive star at 10 solar masses is so luminous it rips through its hydrogen in about 20 million years. Gone. The reason is the mass-luminosity relationship, which roughly says that luminosity scales with mass to the 4th power. So a star 10 times heavier than the sun isn't 10 times brighter. It's about 10,000 times brighter. It burns fuel like it's trying to set a record. Now, the minimum mass to even qualify as a main sequence star is about 0.08 solar masses, roughly 80 Jupiter masses. Below that, the core never gets hot enough for sustained hydrogen fusion, and you just get a brown dwarf. Congratulations, you're a failed star. Here's the important part. Once a star finishes its time on the main sequence, what happens next depends almost entirely on how massive it is. Stars under about 8 solar masses go down one path, a slower, gentler route. Stars above 8 solar masses go down a very different one, faster and significantly more violent. So let's start with the lighter stars. Red giant, so the hydrogen in the core runs out, fusion stops, and you'd think the star would just quietly retire. But the outer layers don't know that. They keep pressing inward, crushing the core, and in response, the envelope bloats outward to hundreds of times its original size. The sun will do this. Models predict it'll swell to roughly 215 solar radii, which is about 1 astronomical unit. That's the current distance from the sun to Earth. So yeah, the sun will expand to approximately where we are right now. The surface cools down to around 5,000 Kelvin, which gives it that red color, but the total luminosity skyrockets to about 3,000 times what the sun puts out today. Cooler surface, way more of it. That's a red giant. Now here's the fun part. Deep inside all that leftover helium that's been piling up in the core, it ignites, not gently. In a degenerate core of about 0.45 solar masses, the helium kicks off in a runaway event called the helium flash. It's almost instantaneous, violently energetic, and the star's surface barely flinches. The outside looks calm. The inside is having a meltdown. And the big question, will Earth get swallowed? Honestly, it's genuinely debated. The sun's expansion reaches roughly our orbit, but the sun also loses about 38% of its mass during this phase, which pushes Earth's orbit outward. Tidal effects complicate things further. It's a coin flip wrapped in a model uncertainty. Either way, the red giant phase is temporary. Once helium burning stabilizes, the star buys itself a little more time, but it's borrowed time. Because what comes next is one of the prettiest ways to die: planetary nebula. So the name planetary nebula has absolutely nothing to do with planets. Early astronomers pointed their terrible telescopes at these glowing blobs and thought they looked kind of like Uranus, which is exactly as embarrassing as it sounds. The name stuck, and now we're all just living with it. Here's what's actually happening. After a low-mass star burns through its helium, it doesn't explode. It exhales. The outer layers of the star get gently pushed outward over thousands of years, forming an expanding shell of gas. Meanwhile, the exposed core left behind heats up fast, sometimes reaching surface temperatures of 100,000 Kelvin. That's hot enough to blast the surrounding gas with intense ultraviolet radiation, which ionizes the shell and makes it glow in vivid greens, blues, and reds depending on what elements are in it. Oxygen glows teal, nitrogen glows red, hydrogen glows pink. It's basically a cosmic mood ring, but here's what makes these things truly wild: the shape. That hot central star is blowing a fast wind outward at roughly 1,000 kilometers per second, and that wind slams into the old, slow, red giant wind that was only crawling along at maybe 10 kilometers per second. Two winds collide, and the gas gets compressed and sculpted into rings, hourglasses, butterfly shapes. Those iconic Hubble photos everyone's seen? That's what's happening. Colliding winds making art, and it's temporary. A planetary nebula only stays visible for a few thousand to about 10,000 years before it disperses into the interstellar medium. One of the most beautiful things in the universe, and it's really just a star's last breath slowly fading away. So what's left behind once the glow is gone? White dwarf. So the nebula drifts away, and what's left behind? The core. Just the core. A ball of mostly carbon and oxygen about the size of Earth, but with roughly half to 70% of the sun's entire mass crammed inside it. The density is around 1 million to 10 million grams per cubic centimeter. That's about 1 ton per cubic centimeter. A sugar cube of this stuff would weigh as much as a small car. You could not pick it up. It would fall through your hand, through the floor, through basically everything. And here's the thing, there's no fusion happening. None. A white dwarf isn't burning anything. It's not a star in any meaningful sense anymore. It's a corpse. A very hot, very dense corpse, slowly radiating away whatever heat it has left. That's it. That's the whole job now. Cool down. Forever. And it really does take forever. A white dwarf with about 0.59 solar masses takes roughly 1.5 billion years just to cool from its initial temperature down to about 7,140 Kelvin, then another 1.8 billion years to drop to 5,550 Kelvin. Eventually, in theory, it would cool all the way down to nothing, a cold, dark husk called a black dwarf. But the universe is only about 13.8 billion years old. Not a single white dwarf has had enough time to finish cooling. Black dwarfs don't exist yet, not one, anywhere. Now, there is one important number to know. It's called the Chandrasekhar limit, about 1.44 solar masses. If a white dwarf gains mass, say from a companion star dumping material onto it, and crosses that threshold, it can no longer support itself. Gravity wins. The result is a Type 1a supernova, a thermonuclear explosion that completely destroys the white dwarf. We'll come back to supernovae soon, but for the vast majority of stars, including our sun, this is the ending. No explosion, no dramatic collapse, just a quiet, slow fade into darkness over timescales longer than the current age of the universe. So that covers the gentle death, but not every star gets to go quietly. Red supergiant. So low-mass stars puff up, shed their layers, and fade out quietly. Poetic, dignified. Now let's talk about the stars that chose violence. Stars roughly 9 to 40 times the mass of the sun don't become modest red giants when they leave the main sequence. They become red supergiants, some of the physically largest objects in the entire universe. Antares, a well-known example, is about 680 solar radii across. UI Scuti has been reported at roughly 1,708 solar radii, though extreme estimates like that carry real observational uncertainty from distance measurements and modeling. But the point stands, some of these stars, if you drop them where the sun is, would swallow Mercury, Venus, Earth, Mars, and Jupiter's entire orbit. Just gone. Despite being absolutely enormous, their surfaces are actually pretty cool, only around 3,400 to 3,900 Kelvin. So they're dim per unit of surface area, but there's so much surface area that total luminosity can hit tens of thousands to hundreds of thousands of times the sun's output. Big and bright, just not efficient. And inside, it's a nightmare. The core is burning through heavier and heavier elements in layers like an onion from hell. Helium fuses to carbon, carbon to neon, neon to oxygen, oxygen to silicon. Each stage burns faster than the last. The final one, silicon fusing into iron, takes about a day. 1 day. After millions of years of fusion, the star's core builds its last element in roughly 24 hours. Red supergiants don't live long to begin with. A few million to a few tens of millions of years total. By the time they reach this stage, they're already on borrowed time. And that iron core, it's about to become a very, very big problem. Supernova. So the star has been fusing heavier and heavier elements in its core, each one buying a little more time. Hydrogen to helium, helium to carbon, carbon to neon, on and on. But then the core starts producing iron, and iron is where the party ends. Every element before iron released energy when it fused. Iron doesn't. Iron fusion actually consumes energy. So the moment a massive star's core fills with iron, fusion stops, radiation pressure vanishes, and gravity wins instantly. The core, roughly the size of Earth, collapses to about 10 kilometers across in under a second. Core temperatures spike above 100 billion degrees. That implosion rebounds, sending a shockwave ripping outward through the star's outer layers, and the whole thing detonates. That's a core collapse supernova. Now here's where it gets weird. The visible explosion, all that light and all that material blasting into space, releases about 10 to the power of 51 ergs of energy. That's an incomprehensibly large number, but it's only about 1% of the total energy released. The other 99%, roughly 10 to the power of 53 ergs, escapes as neutrinos in a burst lasting about 10 seconds. Tiny, nearly massless particles that pass through everything. The entire visible fireworks display is a rounding error on the actual energy budget. There are different flavors too. Type 2. Supernovae are the core collapse kind. They show hydrogen in their spectra and peak at about 10 to the power of 42 ergs per second. Type 1 supernovae are triggered when a white dwarf crosses the Chandrasekhar limit. They lack hydrogen entirely and can peak about 20 times brighter. Core collapse supernovae happen roughly once or twice per century per galaxy. The last one observed in the Milky Way by humans was SN 1054 about 1,000 years ago. We're statistically overdue, though dust probably hides plenty of candidates. So what's left behind after all that destruction? Neutron star. So the star exploded, congratulations, but if the original star wasn't quite massive enough to collapse all the way into a black hole, something survives at the center. And it's one of the most extreme objects in the universe. Take roughly 1 to 2 times the mass of our sun and crush it into a ball about 10 to 12 kilometers across. That's roughly the size of a city. Manhattan, give or take. You now have a neutron star, and the density inside this thing is beyond anything you've encountered so far. We're talking denser than the nucleus of an atom. The matter inside a neutron star is more tightly packed than the core of any atom that has ever existed. A teaspoon of it would weigh about 1 billion tons, so, don't try to pick it up. Right after formation, the interior of a neutron star can reach temperatures of hundreds of billions of Kelvin. It then cools over thousands to millions of years, slowly fading, but still hot enough to glow in X-rays for a very long time. Now here's where it gets interesting. Observed neutron star masses range from about 1.17 to about 2.1 solar masses, and there's a proposed upper limit sitting around 2.5 solar masses. Go above that, and gravity wins. You get a black hole instead. But the exact cutoff, nobody knows for sure. Because the physics of matter at nuclear density, what scientists call the equation of state, is still not fully solved. We're literally unsure how matter behaves when you squeeze it this hard. Current radius estimates land around 10.4 to 11.9 kilometers, but those numbers shift depending on which equation of state model you use. Missions like NICER are actively trying to pin this down. It's a live mystery, and then there's the gap. The heaviest confirmed neutron stars sit around 2.1 to 2.5 solar masses. The lightest known black holes come in around 5 solar masses. So what's in between? That 2.5 to 5 solar mass range is one of the most hotly debated open questions in astrophysics right now. Are there objects hiding in that gap? Are they weird heavy neutron stars, baby black holes, something else entirely? We don't know yet. But speaking of neutron stars doing cool stuff, some of them spin really, really fast. Pulsation. So we've got this ultra-dense, city-sized ball of neutrons spinning in space, but some of them do something extra. They have insanely powerful magnetic fields, around 1 trillion Gauss, and they shoot beams of radiation out of their magnetic poles. As the star spins, those beams sweep through space like a lighthouse. Every time a beam passes Earth, we pick up a pulse. That's a pulsar. And here's the weird part. These things are precise, like absurdly precise. Some pulsars pulse so regularly that they rival atomic clocks on Earth. Scientists actually use them to detect gravitational waves and test general relativity, a violent spinning remnant of a dead star, and it keeps better time than your watch. The universe is showing off, but pulsars do slow down over time. They radiate away their rotational energy, spinning a little slower with each passing year, and when you model that spin down, you need general relativity. Flat space calculations underestimate the power output by up to about 34%. Einstein's equations aren't optional here. They're measurably required. Now, some pulsars go the other direction. If a pulsar has a companion star, it can steal mass from that companion, and the incoming material spins it back up, way up. These are called millisecond pulsars, and the fastest known one rotates over 700 times per second. That's a city-sized medium-sized object spinning faster than your blender. Then there are magnetars. Same basic idea, neutron star, magnetic field, but cranked to 1,000 trillion Gauss. In 2004, a magnetar 50,000 light-years away released a flare so powerful it measurably disturbed Earth's ionosphere. From halfway across the galaxy, one hiccup from a dead star, and our atmosphere flinched. So pulsars are clocks, magnetars are bombs, and both of them used to be ordinary stars. But what happens when even a neutron star isn't enough to hold things together? Black hole. The Milky Way contains somewhere between 100 million and a billion stellar mass black holes. We've directly identified fewer than 100 of them. The rest are just out there, drifting in the dark, invisible unless they happen to be eating something. When a collapsing stellar core is too massive for even neutrons to hold up, typically from a progenitor star above roughly 20 solar masses, gravity wins completely. There's no new pressure mechanism to save it, no degeneracy, no nuclear force, nothing. The core just keeps collapsing, and what you get is a stellar mass black hole. Observed examples range from about 3 to 150 solar masses. Some show up in X-ray binaries where they're actively stealing material from a companion star, and that accretion makes them glow. Others only revealed themselves through gravitational waves, ripples in space-time detected when two black holes spiral into each other. The supermassive ones, a completely different formation category, can reach 1 billion solar masses and are visible as quasars even in the early universe. But here's something unresolved. There's a mass gap between roughly 2.5 and 5 solar masses where we'd expect to find objects, but we rarely do. Are they very heavy neutron stars, very light black holes? Gravitational wave detections are now turning up objects in this range, and nobody's sure yet. It's one of those places where the boundary between two categories gets blurry and physics shrugs. And that's kind of the whole story. A cold cloud of gas collapses in the dark, it becomes a protostar, then a main sequence star, then something enormous or something tiny, then a remnant. The whole life cycle plays out across timescales from thousands to trillions of years. Most of it is invisible. Most of the objects are uncatalogued. The universe is still running the experiment, and we're watching from one small rock, squinting. If you enjoyed this video and want to see more, click the video on the screen now.